Alright, hello class. In this video we're going to be talking about definite integrals, and so this is when we start looking at that connection between this sort of area beneath the curve idea and the integrals that we were looking at as far as antiderivatives go and how they compare. Now we're not going to get exactly what we want here, but this is that first step towards what we're looking at. All right, so the idea of what a definite integral is, well, it actually ends up being the area beneath the curve, or the area between the graph of, say, f of x and the x-axis. All right, so if we recall that the area between the curve of f of x and the x-axis can be approximated by Riemann sums, in other words, using rectangles to get an approximation of what the area actually is. Right? Because the area is approximately the sum of all these rectangles area. Okay? And this approximation is our delta x times some sum of k going from, let's say, 1 to n of f of x sub n, right? Because you would chop this into n rectangles with a base delta x equal to b minus a all over n. Okay? So the idea of what a definite integral is actually taking the limit of this, okay, as either n goes to infinity or delta x goes to 0 to get the actual area. Okay, so if we take the limit as n goes to infinity, that is actually delta x going to 0. Right, so you can think of it as either of these two limits will do the same thing, but what we end up with is that the area will actually equal the limit as n goes to infinity of delta x times the sum of k going from 1 to n of f of x sub n. Okay, and this, you might think that this would be infinite, right? Because this, we're summing up an infinite number of things. However, we're doing that at the same time that we're multiplying by something going to 0. So this limit here is actually a 0 times infinity case, right? And we know that that's an indeterminate form. We know that that can actually go to a number, it could go to infinity, it could go to 0, right? There are lots of possibilities there. So this limit, right, is a definite integral, right? It's the limit of a sum multiplied by a delta x. Okay, so if we rewrite this a little bit, okay, here I've just rewritten it with a delta x, and since this is the same thing, right, over and over again, we can actually move this sort of inside. I'm being a little hand-wavy here. You'll study this in more detail, this sort of idea in more detail in calculus 2. We're just kind of using the basic idea here simply. But if we move this inside, right, and we remember that the same with derivatives, when delta x goes to 0, we write that as a dx instead of a delta x, right? The derivative is dy, or delta y over delta x, where the delta x and delta y are going to 0, so they become a dy dx. So what ends up happening here is this limit goes to a very specific mathematical object that we call the definite integral, and we write it like this. It's the integral sign from a to b, so this gives us the interval of f of x dx. So this should be really familiar. That's our integral sign. And I mentioned when we first learned about it that the integral sign is an elongated S for sum, and that's why. It comes from the infinite sum of these rectangles. And the dx comes from this delta x that's there. Okay, so this definite integral is technically an infinite sum, right? We're summing up an infinite number of things, but we're multiplying it by a factor that goes to 0. Okay, and this is what's called, again, a definite integral. All right, and that definite integral is actually equal, all the way up here, to the actual area beneath the curve. Right, so to give you a graph, the actual area beneath the curve, or between the curve and the x-axis, is actually equal to this definite integral from a to b of f of x dx. Now, I want you to sort of visualize what this is. This is like the base, and this is the height, right? Because we have a very small dx and a height that is given to us by f of x, okay? And that is what our infinite sum is. In Calculus 2, for those of you who are going that far, this is an important idea because this sum of products is basically moving from a constant idea, like we did with displacement versus velocity. With a constant velocity, you just multiply to get to a variable velocity using integration. Okay, you're going to see that pop up a lot whenever you go from a constant multiplication formula, or you have a constant rate times something, and you move to a variable rate times something, integration is going to show up. Okay. Also, keep in mind the idea here that we are basically taking a bunch of rectangles and shrinking down their bases while increasing the number of them. All right, so to show you this on a graph, okay, this is essentially the graph we looked at in the last example. This is basically x squared. Let me, whoa. So this is basically f of x equals x squared. Okay, and here we are with one rectangle, 9, 17, and as we increase in higher and higher and higher, you'll see that we get closer and closer and closer and closer to the actual area beneath the curve. Okay, so, and these are right-handed sums. Now when we do this, we can use either right-handed, left-handed, midpoint. It doesn't really matter because as we let n go to infinity, they're all going to shrink down to be the same, provided that that limit actually exists. You can refer back to the squeeze theorem and what we know about our left-handed and right-handed estimates so far. Okay, and we can take this even further by going all the way out to, say, like 5,000 rectangles. And from here, it looks like it's just the area beneath the curve. So this is 5,000 rectangles, and the area of all those rectangles comes out to be 21.33973376-ish. Okay, so I want to show an example. I want to show this at work with a limit. Okay, so let's take a closer look at what's going on here with a limit. All right, so suppose we want to find the definite integral from 0 to 4 of x squared dx using a limit. Okay, so the idea is that we take the interval from 0 to 4 and split it up into n rectangles, right? N subintervals. Okay, and each subinterval is going to be the length of delta x, and delta x is b minus a all over n. Okay? All right, so that means that this x value is going to be 0 plus delta x, right? And then this one is going to be another delta x, right? So it'll be this plus another delta x, so 0 plus 2 delta x. Then 0 plus 3 delta x. So really, this x value, I've set it up. Thankfully, we started at 0. That makes it easier, but it's going to be delta x, 2 delta x, 3 delta x, 4 delta x, all the way up to n times delta x. Right, and in this case, the n times delta x, well, that would be n times b minus a over n, which would be 4 minus 0 over n, so that would just be 4. So that does actually line up. I chose 0 as the starting point for a reason, just to simplify it. Okay, so what this all means is that this definite integral from a to b of x squared dx is going to be the limit as n goes to infinity of delta x times, okay, the sum of k going from 1 to n of f of basically k times delta x. So I'm using a right-handed estimate. Okay, so this will be delta x times k all squared. Okay, so that's a right-handed estimate. And so I'm going to move this out because this delta x doesn't change, right? The k value doesn't change the delta x, so we can bring that out, delta x squared, and get a delta x cubed out here. And now we have the sum is k goes from 1 to n of k squared. And it turns out that there's actually tables and you can actually prove values for these sums in terms of, say, n. So let me just show you what I'm talking about. All right, so here's a couple of examples of what I'm talking about here. So say we want to sum up a constant from 1 to n. That's going to be c plus c plus c plus c n times. Well, that's the definition of multiplication. So that's just going to be c times n. Okay? This one, if you're summing up k from 1 to n, that's 1 plus 2 plus 3 all the way up to plus n. That actually ends up being n times n plus 1 all divided by 2. In fact, there's a famous story of the mathematician Gauss, who apparently their teacher trying to give them some busy work to do when they were young, told them to sum up 1 plus 2 plus 3 all the way up to 100. And Gauss was able to do it in like a second because he literally did 100 times 101 all over 2, right? Which is 5,050. And you can do it literally that quickly. And he was able to just know that this is the pattern. And you can actually check this. And those of you who are going up to higher math levels, maybe even if you're taking Math 123, you'll learn how to prove these things. Okay? But anyway, the idea is that this sum can be written as n times n plus 1 all over 2. Then if we sum up the k squared, so like 1 squared plus 2 squared plus 3 squared, all the way up to plus n squared, the pattern for that one comes up to be n times n plus 1 all times 2n plus 1 all over 6. Okay? And then we have the pattern for k cubed, so that would be summing up 1 cubed plus 2 cubed plus 3 cubed, all the way up to plus n cubed, and that ends up being n squared times n plus 1 all squared all over 4. And there are a lot of these. There's a lot you can look up, but the tricky thing is that we don't have these for every possible situation that might ever come up, right? So that's why we can't do this every time, right? We do need better methods to approach this, because doing it this way is actually what you would think of as the long way, like doing the limit definition of the derivative. We don't want to always do the limit definition of the definite integral. All right, so I want to label this property here star, right? That the sum from k going from 1 to n of k squared ends up being n times n plus 1 times 2n plus 1 all over 6. And then I want to apply it to where we left off in our calculation, right? Because we have right here, this is the sum from 1 to n of k squared. I want to replace that with what we found, or what we were given in star, right? So this will be the limit as n goes to infinity. I'm going to leave this as delta x cubed. And then here, well, I'm just going to put in what we were given. That was n times n plus 1 times 2n plus 1, all divided by 6. All right, so now if I rewrite this, so remember this delta x is b minus a, and in this case that's 4 minus 0. So I'll write 4 minus 0 over n all cubed times, if you multiply this all the way out, you'll get 2n cubed plus 3n squared plus n all over 6. Okay, so now we're looking at the limit as n goes to infinity of, say, 4 over n all cubed times 2n cubed plus 3n squared plus n all over 6. So this actually comes out to be the limit as n goes to infinity of 4 cubed, which is 64, times 2n cubed plus 3n squared plus n, then n cubed, so all over 6 n cubed. And now if we think back to our infinite limits, right, the limit as n goes to infinity, well, the highest power of n matches on the top and the bottom, so this is going to be an idea with just leading terms. So I have 64 times 2, which is 128, times n cubed, all over 6n cubed. So this limit ends up being 128 over 6, which, lo and behold, ends up being 21.3 repeating, which does line up with what we found here when we went out to 5,000 rectangles. We got 21.339. We're still off by a bit, but the real answer is 21.3 repeating forever. Okay? Now, as I mentioned, this is not something we would want to do every time, right? This is tedious, and it's reminiscent of using the limit to find the derivative. Using the limit definition of the derivative, while that is, accurate and fine, it's not quick, right? It takes a while. So we want to establish a way that we can find definite integrals quickly. Okay, now we will be doing that in the next section. However, in this section, there's a couple more things to talk about. We're not going to do more examples of this method. It's very tedious. But there are situations out there where we can find definite integrals based on graphs if we know a little bit about, say, what's going on. All right, so let's look at some examples like that. All right, so the first complication I want to discuss is what happens when f of x is below the x-axis. Everything we've looked at so far, f of x has been above the x-axis. We want to consider what happens when f of x is below. So when f of x is below the x-axis, right, something like this, we aren't talking about the area beneath the curve anymore. It's more the area, and what I consider more accurate, it's the area between the curve and the x-axis, right? So the integral or the definite integral from a to b of f of x dx, this gives the area between the curve and the x-axis. Okay? And so when f of x is below the x-axis, we're actually mapping this area up to the x-axis instead down to the x-axis. Okay? Now, when we do this, and here's where this gets odd, and I think people start to wonder what in the world's going on, but when we make our rectangles here, all of our f values are going to be negative. Right? So if we go to a graph, and all I've done here, instead of x squared, this is negative x squared. Okay? If I start with a 4 subinterval Riemann sum, things are mapping into the negatives, and you'll see that our area spits out as negative 30. Right, and as we increase the number of rectangles, we're getting closer and closer to negative 21, and it will be 0.33333. Notice we're getting a negative, right? And that does happen. Definite integrals give the area between the graph and the x-axis, but it spits out a negative whenever the function is below the x-axis. Right? So in words, whenever f of x is below the x-axis on the interval a to b, then the definite integral from a to b of f of x dx will be negative. I know that this is sort of different. This kind of goes against the idea of what we think of area. We always think of area as positive. Well, that's still true. This actual area is positive, but the definite integral spits out a negative because it's telling you two things. It's telling you area and direction. Okay, so to write this, your definite area or definite integral is always going to give you two pieces of information. It's going to give you the magnitude A, and that's the actual area between the curve and the x-axis, while the sign, plus or minus, this gives the direction. Right? Are we above or below the x-axis? You can think of this as the difference between velocity and speed. Right? Speed is always positive. Velocity can be positive or negative, and the negative velocity isn't telling you necessarily that your speed is negative. It's telling you that you're going in what we would consider the negative direction. You're falling instead of rising. Right? Same idea here. It gives you the area, but then where is it? How is it positioned in relation to the x-axis? Is it below the x-axis or above the x-axis? Okay, so that's what that is all about, and this is often called the net area. To distinguish it from just area, right? So the net area incorporates negatives, while total area or standard area does not. So net area includes negatives. Okay? So this is also sort of the difference between displacement and total distance traveled. Right? Displacement is literally just the difference between your starting position and your ending position. Total distance traveled is how far you actually traveled, even if you went back and forth. So your displacement could be 0 if you end where you start, but your total distance traveled will always be positive. Okay, that's sort of the idea of what's going on here. All right, so as promised, let's calculate some definite integrals here, and we're going to do so using geometry. And so we're going to use geometry to find the definite integral from 2 to 4 of 2x plus 3 dx. So what do I mean by this? Well, 2x plus 3, or y equals 2x plus 3, is a linear function, right? It has y-intercept 3 and slope 2, right? So if we go over 1, it will go up 2. All right, so the function looks something like this, right? So it's a linear function. All right, and we're looking at the definite integral from 2 to 4. So here's, say, 2, and here's 4, and so we are looking for this area in here, which is essentially going to be a trapezoid, right? Or, if you prefer, it's going to be this rectangle with a triangle on top. And so we can actually use geometry to calculate what this definite integral is going to be. So this area is actually equal to the definite integral 2 to 4 of 2x plus 3 dx. Okay, so how we find these heights? Well, f of 2, I didn't really draw this to scale necessarily, right? So don't pretend like I did. But you could just plug 2 in to get this height. So this height, when we plug in 2, that'll be 4 plus 3, so that's going to be 7. So this is a rectangle that is a 2 by 7. Okay. So I'm going to put 2 by 7 in here. And then this triangle, well, if we want to figure out how high or what the height of this triangle is, now we can put in 4. So when we put in 4, we'll get 8 plus 3. So this will be 11, meaning the height of this triangle itself is going to be 4. Okay, so this is a 2 by 4 triangle, right? So we have a 2 by 7 rectangle plus a 2 by 4 triangle, right? So when we talk about the area, that's going to be the area of the rectangle, that's just 2 times 7, plus the area of the triangle, which will be 1/2 times 2 times 4, right? The area of a triangle is 1/2 base times height. Okay, so looks like we'll get 14, plus these 2's will cancel, 4, so 18. So the definite integral of this function from 2 to 4 is 18. Okay, so that's what I mean when I say we can use geometry to find the definite integral of a given function. All right, let's look at another example. Let's say we want to use geometry to find the definite integral from 1 to 6 of 2x minus 6 dx. So instead of graphing it by hand this time, let's look at the graph on software. 2x minus 6 is this line right here. Okay, and if we're looking at the definite integral from 1 to 6, we're basically talking about this shaded area right here. Now notice, part of it is underneath the x-axis, and another part of it is above the x-axis. So anything below the x-axis is going to be negative, anything above the x-axis is going to be positive. So this triangle is a 2 by 4, right? So that's our first triangle, and then the second triangle is a 3 by 6, it looks like, based on the graph. All right, so based on the graph, the net area is 1/2. Now, you can always get the right answer if, when you put in the height, you make the negative ones a negative. Right? That's probably the easiest way. So it'll be 1/2 base, which is 2, times height, which is negative 4. So 1/2 2 times negative 4. Okay, then it will be plus the area of the second triangle, which in this case will be base 3 and height 6. Okay, so it'll be 1/2 the base times the height, which is 6. Okay, so these 2's will cancel, so we'll get negative 4 plus 1/2 times 3 times 6, so that's going to be 9. Okay, so the net area comes out to be 5. If you wanted the total area, well, you would just do what you're used to doing and make everything positive. Right, so the total area would be
you basically take the absolute value of everything. Right, so you get 4 plus 9, which will be 13. However, the definite integral doesn't care about the total area. It gives the net area. Okay? All right, so for our next example here, let's use geometry to find the definite integral from -2 to 2 of the square root of 4 minus x squared. Now this one's a little tricky. If you think of y equals the square root of 4 minus x squared, and you square both sides, you'll get y squared is equal to 4 minus x squared. And then if you move that x squared over, you get x squared plus y squared is equal to 4, which we could also write is 2 squared. So this is the circle of radius 2. Okay, but since we started with the plus square root, this is the top semicircle of radius 2. Okay, so what we're looking at here is basically from -2 to 2 of this semicircle. So here is our square root of 4 minus x squared. And so the definite integral is this area here. So there's nothing below the x-axis, just stuff above the x-axis. So we're going to get a positive definite integral. And, so the definite integral from -2 to 2 of square root 4 minus x squared dx, well, it's going to be the area of this region. So it's going to be the area of half of a circle, right? So it'll be 1/2 times pi r squared. Our radius here is 2. And so there we go. We get 1/2 times pi times 4. So it ends up being 2 pi. All right, so there we go. So thankfully, we aren't going to be using limits to calculate definite integrals here. We're mainly going to be using geometry. And then in the next section, we will talk about how we can do it for other functions without needing geometry to do it. However, sometimes geometry is the best way to go if we're talking about like a linear function, right? It's very easy to just graph it and use triangles and whatnot. Okay, so let's suppose that we have this graph here, f of x from 2 to 9, and we know what the total areas are on the inside, right? So the total areas, not net areas, are given. Let's say here it's 10, here it's 4, and here it's 2. Okay, so using this graph, we want to find the definite integral of f of x from, let's say, 2 to 6. Okay. Well, we're just really talking about this region right here, right? 2 to 6, the area between the graph and the x-axis is this, and we're told that that is 10. Okay, so 10. Okay, now let's look at the definite integral for between 2 and 8 of f of x dx. Well, here now what we're talking about is this region plus this region. But since this region here is below the x-axis, the definite integral, okay, of this is going to be our 10, then plus the net area here, so we're going to actually get -4. Right, so it's going to be 10 minus 4, which is 6. Now, how would we get the total area if we wanted it? Okay, well, if we wanted the total area, what we would need to do is take the definite integral from 2 to 8 of the absolute value of f of x dx. Okay, so what that does is the absolute value takes anything that's negative and flips it up to be positive. So this is the absolute value of f of x. So it doesn't change anything here because it's already positive, or here, but here it would. Okay, so if we wanted the total area, it would be the definite integral from 2 to 8 of the absolute value of f of x dx. So that would be 10 plus 4, or you can think of it as taking the absolute value of everything. So absolute value of 10 plus the absolute value of negative 4, which would be 10 plus 4, or 14. Okay, so that's different than the definite integral, which is the net area. Okay? Then if we just look at the definite integral from 6 to 8 of f of x dx, that is, of course, negative 4. So that brings us to something very important here, is to note that the definite integral from 2 to 8, right, of f of x dx, is the same thing as taking the definite integral from 2 to 6 and then summing up the definite integral from 6 to 8. Right, you can always do this. So if it's beneficial to you to split up a definite integral like this and do it in pieces, go right ahead. We can do that with areas, so we can do it with definite integrals. Okay? So finally, that leads us, I'll do it up here since things are getting cluttered. If I wanted the definite integral from 2 to 9 of f of x dx, it would be positive 10 minus 4 plus 2, right? This region minus this region plus this region. Okay, so it would actually be 10 minus 4, which is 6, plus 2, which is 8. Okay? All right, so that is actually the majority of what we need to talk about in this particular section. There's a couple of final little quick things I want to mention before I end things, but this is essentially what this is all about. There's a lot more to unpack, but I think a lot of that will just become clear as you work through the homework versus me just reciting it to you. However, okay, so the first thing I want to mention is if you reverse the limits of integration, so if you do the integral from b to a of f of x dx, that's actually the negative of the integral from a to b of f of x dx. And the reason that is if you're reversing the order, so if you think of it in terms of, say we're on an interval a to b, and you're splitting things up, and you have your delta x. So remember, delta x is always your b minus a all over n. If you reverse the order and you start thinking about it in terms of this way, right, you do a to b, or a minus b over n, that's actually going to be negative of b minus a over n. So if this is the positive value, your delta x has now become negative, and so that's pretty much why that's happening. Okay, and then this pops up every so often. Sometimes it's easier to just flip the order of integration and throw in a negative. I think we'll see some examples of that in the next section. And then if you're trying to integrate from a to a, right, from 1 to 1, 2 to 2, that is always going to be 0, right? Because if you're going from a to a, there's no area. Right? You can't have an area with base 0. So this is base equal to 0. So 0 times any height is going to be 0 unless you have an infinite height, which we are not assuming here. So that's the other little quick property I wanted to get out of the way before we move on to how we actually evaluate these definite integrals without the need of geometry. Okay, so I will see you all in that next video when we tackle that, and I'll talk to you then. Cheers.